Okay, we are now at 11 o'clock. Good morning, everybody. Welcome to the webinar on CNL's nuclear power demonstration closure project. Today's topic is assessing the long-term safety of the NPD disposal facility. My name is Mike Giardini. I'm a communications officer with CNL's stakeholder relations team. And yeah, we have a good group of attendees. Our apologies for getting the timing changed from the NRT article, if you did see that, but I see quite a few people on, including my mom. Hi, Mom. All right. So before we get started, I'd like to acknowledge that the NPD site is located on the unceded and unsurrendered territory of the Algonquin Anishinaabe people. As an organization, CNL recognizes and appreciates Indigenous peoples' connections to these places. CNL also recognizes the contributions that First Nations, Métis, Inuit, and other Indigenous peoples have made, both in shaping and strengthening the communities where these projects are situated and the country as a whole. So today's webinar will include a presentation, and then we'll open the floor for a Q&A discussion period. A few housekeeping items. There is simultaneous interpretation. If you'd like to listen in French, please hit the globe icon on the bottom right of the bar and select the language you'd like to hear. It will take about an hour today, 30 minutes for the presentation, and then we'll leave 30 minutes for Q&A. The Q&A icon is the way that you submit your questions. You can submit them in writing, and then we will take them up at the end, but you can ask them at any time throughout, and we'll take them up at the end. We will be recording this session and posting them on our YouTube channel afterwards for people that cannot make it at this time. And if you're having any issues or you would like to chat outside this discussion, please email ermstakeholder@cnl.ca and we will try and get you sorted out. Now I will introduce our first presenter, the manager of NPD regulatory approvals, Katie Shorter. Katie.
Good morning. Thanks, Mike. Welcome, everybody. Before we jump into the presentation for today, I just wanted to remind everyone that our past webinars are available on CNL's YouTube page. And we've covered quite a range of topics. So we've talked about our environmental impact statement and the changes we've made. We've presented information about waste inventory. We've discussed species at risk, the safety barriers, our safety case, and we've also talked about follow-up monitoring. So we've tried to focus those topics on areas of interest or concern that we've heard during our engagement work. But if there are other topics that you'd like to hear about coming up at our webinars going forward, please reach out to ERM stakeholder email, and we can certainly prepare something on topics that are of interest to people. Next slide, please. So as Mike mentioned, I'm Katie Shorter. I'm responsible for the NPD closure project. Today, we're going to talk about safety assessment, specifically the long-term safety assessment for our proposed NPD, or nuclear power demonstration disposal facility. So today you'll get to hear from myself, but also our project's safety analyst, Graham Porter. And he's going to help explain how we've structured our safety assessment and the different events that we consider. Topics that are going to be covered today are a little bit of a reminder about what we're proposing for the decommissioning of the NPD facility, which is in situ disposal. We're going to go over the regulatory requirements and assessment framework for the safety assessment. We'll talk about acceptance criteria, which are the criteria we use to compare our results. We'll highlight the components of our model, explain our normal evolution scenario, and talk about the different pathways and receptors that are considered. We'll also describe some of the environmental or human disruptions that could affect the facility, and then we'll highlight some of our results. Lastly, there'll be an opportunity for you to ask questions. As Mike mentioned, You can use the Q&A function and you can submit those questions anytime throughout the presentation. We'll talk through them at the end. So this slide just helps remind everybody about the history of NPD and the work that we've done here so far. So in 1957, construction began at the site. And in 1962, we made history at the NPD site when we generated electricity from nuclear power for the very first time in Canada. So for 25 years, the site produced carbon neutral energy and operated as a training center. In 1987, the reactor was safely shut down and the first phase of decommissioning began. At that time, we removed the fuel and transferred it to safe storage at the Chalk River Laboratories, and other systems were drained, including heavy water. The non-nuclear power generating equipment was removed, along with some redundant buildings that were demolished. Since that time, the site has been in a period of storage with surveillance. Now we've reached the point where we want to complete the decommissioning. We've proposed to do that via in situ disposal. Right now, the project is undergoing an environmental assessment, and we've requested a license amendment from the CNSC, the Canadian Nuclear Safety Commission, for approval for that decommissioning work and the creation of an in situ disposal facility. In situ disposal means that we want to dispose of the waste that is here at NPD in place. The entire above grade structure will be demolished and all debris from the demolition will be placed in the empty spaces that are below grade. The demolition debris, the remaining reactor components, and the existing waste and inventory at NPD will be completely sealed by filling the underground structure with a specially formulated grout that will contain and isolate contaminants, ensure stability, and reduce corrosion. The grouted structure will then be capped with a reinforced concrete cap and covered with an engineered barrier. CNL will continue to monitor the site and surrounding environment post-decommissioning for a minimum of 100 years to ensure that the disposal facility is performing as intended and that people in the environment remain safe. One of the things we will be doing is keeping the ventilation stack in place as a habitat for the protected species, the chimney swift. CNL would not recommend in situ disposal for every reactor, but certain facilities like NPD are well suited to in situ disposal. The NPD structure sits 25 meters below grade and is constructed into the bedrock. The existing facility consists of thick, in some places up to 3 meters thick, reinforced concrete walls and floors, and the main components are trapped within the corrosion-resistant metals of the reactor. These components working together are part of the reason why in situ disposal is an appropriate choice for NPD. So our proposed in situ disposal strategy for NPD will result in the creation of a permanent radioactive waste disposal facility. So the relevant Canadian regulatory document is shown here. It's Reg Doc 211-1, Volume 3. It's called Safety Case for the Disposal of Radioactive Waste. And the main technical component of our safety case is the post-closure safety assessment, which we'll talk about today. The post-closure safety assessment forms the core of the safety assessment for a disposal facility. It involves an analysis of the expected normal evolution of the disposal system, possible disruptive events, and the potential radiological and non-radiological impacts on people and the environment. Scenarios are used to describe possible evolutions of the system and its environment, as well as impacts. The regulatory document states that the applicant should apply models to each given scenario to assess the evolution of the waste form and associated contaminant activity concentrations over time, contaminant releases and release rates, the evolution of the engineered barriers, changes to natural barriers, contaminant transport through the engineered barriers, the geosphere and the biosphere, and receptor exposure. There are also other applicable regulations and guidance One being Reg Doc 211, which is the overarching framework for radioactive waste management and decommissioning in Canada. And there are also several IAEA safety standards that are applicable. Disposal of radioactive wastes, IAEA SSR 5, and IAEA SSG 23, which is the safety case and safety assessment of disposal of radioactive waste. So now we're at the point where I'm going to turn things over to my colleague Graham, and he's going to walk you through our safety assessment.
Thanks, Katie. Evaluating post-closure safety requires projections of the future condition of the disposal facility and its environment, and how people might interact with that facility. Systematic approaches have been developed to undertake such evaluations, and they're centered on a system analysis method. This involves representing the disposal facility, the contaminants present, and all potentially relevant media with mathematical models to represent the key processes that may occur. For example, corrosion of waste, dissolution into groundwater, and uptake by plants, plus other things. It's essential that the models are relevant, well-grounded, and auditable. This is achieved through a systematic approach to safety assessment. The international community has developed best practice guidance on the process, which is documented in a report from the Improvement of Safety Assessment Methodologies, which is called that, usually abbreviated to ISAM. And it's a program of the International Atomic Energy Agency. In addition to this, there's a features, effects, and processes list. This was developed in a systematic manner following the Nuclear Energy Agency International FEP list, and it's based on the following 5 categories. So category 1, this covers external factors, and these are processes with causes or origins outside the assessed disposal system. Category 2, which is waste package factors. This is all factors related to waste packages, the associated releases, and the migration of contaminants through this facility. The third category is facility factors. This looks at things such as excavation, damaged and disturbed zones, site investigation, monitoring boreholes, etc. A fourth category that addresses geosphere factors. Again, these things are mechanically undisturbed areas around the facility, so basically undisturbed environment, and the associated migration of contaminants. And the final 5th category is biosphere factors. This is the surface environment, and it looks at things as humans, non-human biota, and the associated migration of contaminants through the biosphere. In total, over 200 FEPs were compiled and reviewed for their relevance to the NPD waste facility and categorized using a systematic screening process, taking into account potential consequence and their likelihood of occurrence in the future. The latest FEPS version was published in 2019, and the initial 2014 FEPs that were used in the project have been compared to this revised list. The comparison indicates that many of the FEPs are equivalent in the 2 FEP lists, although there are some differences. The difference between the revisions have either been addressed by either the new 2019 FEP or addressed by the previous 2014 ones. A screening analysis of the additional FEPs in the 2019 FEPs found that the additional FEPs can be screened out and don't have any impacts on the work that's already been previously done. Next slide, please. Acceptance criteria are derived from current regulatory limits, standards and objectives and benchmarks. Where appropriate, an additional margin of safety such as a dose criterion has also been applied. In light of the Canadian regulatory requirements and guidance and the international standards and guidance from organisations such as the International Commission on Radiological Protection, specific criteria have been proposed for the potential radiation exposure that may arise from the expected evolution of the NPD disposal facility and its environment, referred to as the normal evolution scenario. The potential radiation exposure that may arise as a result of events with uncertain or low probability, which could disrupt the facility, and these are referred to as disruptive events. The potential radiation effects on non-human biota and the potential effects of non-radioactive materials. Human health criteria have also been defined according to the appropriate regulatory documents from the CNSC, for example, CNSC Reg Doc 211.1. And this requires reasonable assurance that the regulatory radiological dose limit for public exposure of 1 millisievert per year will not be exceeded. It also includes the possibility of exposure from multiple sources is considered, and that doses are as low as reasonably achievable. As mentioned, the project is constrained by the dose limit set by the CNSC, which is that through the normal evolution of the facility, annual doses shall not exceed 1 millisievert to any member of the public. Further, it states that a lower constraint be set to account for the public receiving other doses from other sources, i.e. a cumulative effect, and recommends a value of 0.3 millisieverts. The project sets a constraint of 0.25 millisieverts per year as a dose constraint for the normal evolution scenario. In both cases, the projected project doses to the public are incredibly low and orders of magnitude below the project constraint. For disruptive events, the dose constraint is the IEA reference level of 20 millisieverts, and the impact from disruptive events, including human intrusion, do not exceed these for reference levels. Next slide, please. This is all represented by the use of a mathematical model and to describe the NPD disposal facility. And this comprises of mathematical representations of the existing concrete structure, including its geometry and rooms, the grout backfill within the structure, metal components such as the calandria, and we make distinctions between aluminium, carbon steel, stainless steel, and zircaloy. The activated concrete walls of the reactor vault, surface contamination present on structure surfaces that will remain in the various rooms is also modelled. Chemical contaminants such as lead from things such as lead paint and shielding and mercury, they're included in the model. The reefs pathway and geosphere from the facility to the river and the surrounding biosphere is also modelled. In addition to this, detailed groundwater modelling was used to account for important site features, such as the cooling pipe trench, tile drains, and overburden characteristics. For example, the cooling pipes will be sealed with concrete and do not provide a direct pathway, but the trench they travel through will continue to act as a preferential below-grade pathway for facility releases to flow through. The baseline for the analysis in the mathematical model is a normal evolution scenario, and this has been modelled using the following features. The facility is closed as planned with no unforeseen events. A period of institutional control is initiated, and that lasts for at least 100 years, during which the facility remains under surveillance and no human intrusion occurs. At the end of the institutional control, we assume that an earthquake occurs that's equivalent to a 1 in 2,250 year magnitude earthquake. And a 1 in 10,000 year earthquake happens at about 1,000 years following closure. We also assume that the climate evolves according to the current best knowledge of climate change. This is anticipated to include global warming of several degrees centigrade, deferring the next scheduled ice age beyond 100,000 years from now. Generally, the environment is assumed to remain broadly as it is at the present day. At closure, the facility will be filled with grout. The whole facility gradually fills with groundwater. This will slowly flow through all the pores of the concrete and grout. Once it reaches the waste, contaminants can dissolve into the groundwater. Surface contamination and contaminated aluminium is assumed to dissolve instantly, but radionuclides embedded in steel and zircaloy are only released at the rate of corrosion of the metal. The high pH of the pore water in contact with cementitious materials will result in very low corrosion rates of these metals. The radionuclides in groundwater will partition between the water and the solids according to their characteristic properties, represented with a sorption coefficient in the model. The rate that the disposal facility fills with groundwater will be controlled by the hydraulic conductivity of its walls and the grout backfill. Hydrogeological calculations indicate that this period of resaturation may occur quickly and take several decades to complete. During the resaturation period, contaminants will only be released from the facility by diffusion, as groundwater will be flowing into the facility and not out. The low hydraulic conductivity means that the flows into and through the facility will be very small, around about a few meters cubed per year. In addition, the water will be alkaline with contact from the cement. This increases the sorption of some radionuclides, which reduces the rate at which they can migrate. Over time, the facility will gradually degrade, taking more than 10,000 years for complete chemical degradation of the cement. Groundwater flows in the vicinity of the disposal facility are predominantly at the base of the overburden, but with a significant component of flow in the bedrock. The tile drains initially deflect much of the groundwater around the facility until the end of institutional control. This is conservative as it provides a rapid transport pathway for any contaminants released. Down gradient to the facility, groundwater flows towards the river and discharges at the riverbed, close to the shore, following a preferential pathway caused by the cooling pipe and trench. When the drains fail, springs may emerge from the overburden close to the shore. Some contaminants are expected to be transported through the bedrock. The concentration of the contaminants in the groundwater will nevertheless be very low due to their low rate of release. Contaminants released into the Ottawa River may sorb to sediments or may be taken up by aquatic flora and fauna. The dominant process will, however, be advection, dispersion, and subsequent dilution in the water. Variations in the river level have been taken into account due to climate change, flooding, and changes in rainfall. Water is assumed to be extracted from the river to be used for drinking by people and livestock, and also to irrigate soil for crops that are subsequently eaten. Radionuclides in the irrigated soil are a source of external irradiation to the local resident community living there. Members of the local resident community are also assumed to source fish from the river and be exposed to contaminants sorbed onto bank sediments. They may also swim in the river and use it for washing. In addition to this, a local resident community, i.e. people living downstream and using water from the river, can be exposed to contaminants released into the river water. As such, downriver public receptors are included among the receptors assessed. As a result of Indigenous stakeholder feedback, the normal evolution scenario also examines the Indigenous receptor intended to represent a traditional Indigenous lifestyle. I should just hand over back to Katie for the next slide.
Thanks, Graham. So Graham's actually started talking through a lot of the things that are represented on this slide. So the models, the mathematical models that Graham described a couple slides ago, predict the concentrations of contaminants that will reach the environment surrounding NPD. These environmental media, air, surface and groundwater, soil, and sediment, form the pathways by which receptors, people, and biota can be exposed to contamination. So on the right-hand portion of this slide, the mechanism by which receptors are exposed to contamination in each pathway is briefly described. For example, surface water. As Graham noted, the model predicts springs close to the river. These would not be suitable for drinking, but can contaminate the soil immediately surrounding them. The river itself can be used for drinking, crop irrigation, bathing and swimming, and these are all exposure routes. Some biota live or spend time within the surface water, such as fish, aquatic plants, and waterfowl. The biota is exposed to contamination and in turn could be ingested by humans. Finally, livestock and wild animals drink from the river and could be eaten by humans. The image on the left-hand side shows 4 human receptor groups. These are the ones that are considered in the long-term assessment and mentioned by Graham already. On the left-hand side, an Indigenous group. At the top, an on-site resident. In yellow, individuals using the area for recreational purposes. And on the right, in purple, an off-site receptor. The dotted white lines are showing the pathways which contribute to the overall predicted dose for the receptor. So the site resident group represents a small family that lives on the site of the facility and obtains all their food from the immediate vicinity. The exposure of this group is maximized by assuming that they obtain water from the river and use it to irrigate crops and drink. They also raise livestock, which drink water from the river, fish the river, and use it recreationally. Next, the recreational user, represented in yellow, is using the area around the NPD site for recreational activities. The exposure pathways include obtaining wild food from the region of the facility. This receptor isn't assumed to live on site. Next, the Indigenous group has habits based on a recent diet and harvest study from a local Indigenous community. This study shows that today, diet is likely to be supplemented with additional groceries purchased from local shops. This receptor group, however, does consider the same exposure pathways as the recreational user, obtaining some food from wild animals. And it also considers exposures that are related to more traditional use of materials harvested or gathered from the surrounding area. These pathways include inhalation of smoke from burning medicinal plants and rubbing of plants into the skin. Finally, the offsite receptor is also considered living downstream of the NPD and using the river water for drinking and washing. I'm going to pass it back over to Graham, and he's going to talk a little bit about some of the environmental and human disruptions that might happen to the NPD in the future.
Thanks, Katie. Okay, in evaluating the safety of the project, the predicted models are run through a wide variety of scenarios. This is to understand the likely impacts, the potential impacts, and the relative importance of various features of the facility in overall safety. These are grouped into the normal evolution scenario, which is a general conservative representation of the expected long-term evolution of the site and the receptors that may be exposed to it. It is unique for each site in certain respects, such as how domestic water might be obtained by a future receptor. Additionally, disruptive events are also considered. These examine the potential impacts from unlikely but plausible events that can alter the normal evolution of the site, such as an unexpected seismic event, human intrusion, or even glaciation. And these are what have been developed from the features and effects process analysis was done earlier. These help to understand, to demonstrate the robustness of the system to handle more extreme events, even though they are unlikely to occur. There are approximately 6 disruptive events considered. So site investigation, that's a disruptive event scenario that represents the possible consequences of people in the future, locating and investigating the disposal facility without knowledge of its contents. It's basically a human intrusion scenario. A flood case assumes that a flood or erosion event occurs after the 100 years of institutional control, leading to scouring of the surface and people being directly exposed to the rock that has been contaminated by groundwater. A further event is extreme degradation. So the structure of the disposal facility and the grout plan to be added both physically limit water flow through the waste and also provide chemical conditions that limit the release of radionuclides. So this scenario examines the consequences of the extreme degradation of these barriers. A further event is fault zone activation. So this disruptive event case builds on the assumptions made in the extreme degradation case to represent even more comprehensive damage to the disposal facility, as well as a higher conductivity in the bedrock due to a fault zone being reactivated. A further disruptive event is excavation of the above bedrock facility. So this scenario examines the impacts of the above bedrock portion of the facility being excavated. And the final disruptive events considered are a well scenario, of which this can be broken down into 2 variations. So a well provides a route by which radionuclides in the groundwater can be ingested in drinking water and also used to irrigate soilets for farming. So the 2 cases we consider are the overburden well. So this case examines the impacts of the resident receptor using an overburden well intersecting water in the pipe trench. And the bedrock well, in this case, examines the impacts of the resident receptor using a bedrock well intercepting the bedrock release plume between the facility and the river. Next slide, please. IEA guidance SSG 23, which is the safety case and safety assessment for disposal of radioactive waste, advocates an iterative approach to a safety analysis. For the development of the post-closure safety assessment, an iterative process has been adopted. This approach was used to refine the analysis as progressively better data was obtained as the project has been developed. The iterative process also allowed the scenarios identified and developed early in the process to be refined, depending on the results obtained, and to reduce uncertainty with the analysis. In summary, the iterations have refined the safety analysis as additional data was obtained. So the scenarios identified and developed early in the process have been refined to reduce uncertainty and reduce conservatism of the analysis. And they've also built upon the experience, knowledge, and review comments from earlier iterations. Also, due to the long timescales involved, some uncertainties surrounding the analysis exist, and the use of multiple iterations has reduced the uncertainty in this data as it's been refined. As mentioned earlier, the dose criterion for normal evolution is 0.25 millisieverts per year. And for destructive event scenarios, we use a criterion of 1 millisievert per year. So the results of the revised analysis, which is basically the fourth iteration of the post-closure safety assessment, show that the doses are significantly below the acceptance criteria. There is one exception to this, as you can see from the figures here, and this is the mass excavation scenario. But if we use the guidance given by the ICRP and the IEA, and then which said if the calculated dose exceeds 1 millisievert per year, and taking into account the likelihood and nature of the exposure, conservatism and uncertainty in assessment, and also conservatism in the dose rate criterion, then if the probability of exposure can be quantified, a reference health risk criterion of less than or equal to 10 to the minus 5 per year can be used, and this is documented in SSG IEA document SSG 25, which is near surface disposal facilities for radioactive waste. In this what-if case, the health risk criterion is considered to be met due to the extremely pessimistic assumptions used in developing the scenarios. Next slide, please. And basically that concludes our presentation. So we're now open to if anyone has any questions, and I'll hand back to Mike.
Okay, thank you, Graham and Katie. So yeah, if anyone would like to ask questions, please use the Q&A function, and we will wait for a few to come in. Okay, so here is one to get us started. How is CNL so sure that the NPD facility is safe in the long term?
I'm happy to take that one.
Thanks, Katie.
So in our presentation today, we talked a little bit about the barriers that there are to contain and isolate the contaminants. So there are natural barriers, the bedrock, and man-made barriers like the concrete. So as noted, the facility was built into the bedrock, and that's stable and typical of the Canadian Shield, 25 meters below grade. We have the concrete construction of the original reactor facility, the thick concrete walls of the reactor vault, and the building structure itself. These are also barriers. Another benefit is that the properties of the waste are well known. They've been extensively characterized early in our decommissioning work. And the contamination is actually trapped. It's embedded within the waste material itself. And those metals, the zirconium alloys and the stainless steels, are meant to be corrosion resistant. Our post-closure safety assessment looks out to 50,000 years. And at that point, 98% of the radioactivity remains in the facility. So why do we think it's going to be safe in the long term? We know that we have multiple barriers in place to isolate and contain the waste. And as you saw on the last slide, the predicted doses for the different scenarios that we've modeled are extremely low, much lower than the dose criterion we've set for ourselves. Thanks, Mike.
No problem. Thank you, Katie, for that answer. The next one is 100 years of institutional controls. What kind of controls exactly?
I can answer that one, Mike.
Okay.
Yeah, for the 100, well, it's going to be at least 100 years. We expect it to be significantly longer than 100 years of institutional control. It's just that 100 years is used in the model as a conservative assumption. Things like for the period of the institutional control, we will have things like the facility will be fenced and there'll be monitoring in place. So there'll be regular inspections, so they're preventing people coming in, accessing the area, so the facility will be repaired. There are other things as well, like there'll be land use controls where it will be recorded on the land deeds that the land is actually classed as a hazardous waste disposal facility. So there's lots of things along those lines. So, but the main thing will be that like it remains under control of under our control at that time, and that people will not be able to have restricted access to it, and they won't be able to actually do any intrusions to the area. Okay.
Okay, thanks, Graham. The next one is, could you explain a little more on the discharge to river in the geosphere model? And that one, that will be Katie.
Thanks very much, Mike. So this is a great question. The studies of the surrounding geology that we have performed show us that there are two main pathways where the groundwater flows and where contaminants will be released. So the one is through the overburden, and there's a preferential pathway through the pipe trench that travels to the river. And the second pathway is in the shallow bedrock. So again, through the studies of the site that we've done, we know that bedrock pathway, the discharge point is actually in the bed of the Ottawa River, just offshore of the NPD site. So that's where the discharge happens within the Ottawa River. This is quite an interesting technical topic. So maybe I can suggest submit your question again through ERM stakeholder relations, and maybe it's an opportunity for you to meet with some more of the technical team to discuss it in more detail.
Okay, thank you, Katie. The next one, I believe you'll answer as well. Are CNL planning to execute the NPD decommissioning work themselves, or will CNL be looking for support from contractors?
Thanks very much for this question. The plan right now is for it to be a combination. We have resources at our Chalk River site who've been doing a lot of building demolition work. And so some of that team will help with the physical demolition activities at NPD. But we do expect to engage a contractor to support the grouting work and the installation of the cap and cover.
Okay, thank you. The next one, what is the basis for the dose criteria / limit?
So I can start that, and I think Graham will probably take over in a minute. But the initial basis is the 1 millisievert public dose acceptance criteria from the CNSC, and the 0.3 millisieverts that's suggested by the ICRP to consider multiple sources. We've actually cut that down just a little bit more to the 0.25 millisieverts. And I think Graham can talk more about the criteria that we use when we're considering disruptive events. But the basis really is the Canadian regulatory limit for the public.
Yeah, thanks, Katie. Yeah, the one for the disruptive events, it's a slightly different thing. That comes from the IEA documentation. I think it was, I said in the presentation, I think it was SSG 29. I could be wrong on that one, but basically that says that if you have doses up to, I think it's 20 millisieverts, in excess of the 1 millisievert dose criteria anyway, if it has a really low probability of occurrence and the health risks associated with that come out to be the risk of like killing death to someone is a lot less than 10 to the -5 per year, then you can consider that you've done enough on the barriers and human intrusion scenarios and things, and modelled it well enough that that dose is acceptable, or the risk from that scenario is acceptable. Thank you.
Okay, thank you both for that, for those answers. The next question is, can you explain the difference between leaving everything as is versus in situ disposal?
I can take this one. So in a situation where we leave everything as is, we still have a license with the CNSC for the NPD site. So we would maintain the facility in a safe state. One of the things that starts to happen as time goes by is the building structure starts to deteriorate, and there's costs to maintain and keep that facility safe. The real difference with the in situ disposal is that we are adding the grout, adding a cap and cover, and putting the facility in a state that's passively safe. We will monitor it to make sure it's performing as we expect it to, but it's a permanent way to leave the site that's containing and isolating that waste so that ongoing costs and human intervention essentially go away.
Okay, thank you for that. The next question is, are you still planning to remove the building in 2026?
I can take that one too. We didn't talk a lot about the project timeline today, other than to say we're working through the environmental assessment and the license amendment change. But our schedule right now is that we still need to submit to the CNSC, the Canadian regulator, an updated environmental impact statement. The CNSC and the federal review team has another opportunity to review that material and ask additional questions. And then we would submit a final EIS, or environmental impact statement, to address all those questions. At that point, we would move toward a hearing. So our current schedule projections would have a decision, the hearings and a decision happening in 2026. So if it was a positive decision, decommissioning activities, the demolition of the building would occur after that point. So 2 to 3 years of physical decommissioning work after we get approval, starting late in 2026. That's the timeline right now.
Okay, I'll just follow up on the same topic with another question that came in. What about the timeline for cap and cover and completion of the decommissioning work in the field?
Okay, I think I've answered that one, but just for clarity, as I mentioned, we can't proceed with our decommissioning work until there's approval. We expect to get that sometime in 2026. So the building itself comes down, the material is size reduced and added to the, or put in place below grade in the empty spaces, and the grout is added. The cap and cover is the last step in essentially closing the disposal facility that we've created. So timing wise, that decommissioning execution timeframe is expected to be 2026 to 2028 or into 2029. That's the timeline.
Okay, thank you. Next question is, why is full removal of the waste not proposed?
So full removal of the waste is one of the options, one of the alternatives that CNL considered. So we looked at essentially a do nothing is a wrong terminology, but a continued storage with surveillance as an option. We looked at partial dismantling, so removing some of the material. We looked at the full dismantling option, removing everything. and we considered the in situ disposal option, which is the option that came out on top in our evaluation of the alternatives. And that's the proposed decommissioning strategy that we've put forward right now.
Okay, thank you, Katie. Just going to wait for more to come in. So there is one that is on the regulatory limits and how Canadian goes up against the EU and the US. But I suggest probably going on the CNSC website for more information on that. Okay, so we still have a bit of time, so I will continue on. A question about the calandria. Will it be broken down and removed, or will it be cut up and moved into below ground rooms, or what's the idea with the calandria?
So the in situ disposal strategy has all the waste that exists at NPD right now, which is the empty metal systems of the reactor, the concrete structure itself, and eventually the above grade structure. That's the waste. The plan is for all of that material to be disposed of in situ, so to stay in place. So there is no plan to cut the calandria and remove it topside or to move it anywhere else below grade. As part of our decommissioning steps, we have activities to cut access points in major pipes, cut access points through walls and floors, and that's to allow the grout to get into as many spaces as possible. So no cutting of the calandria is planned, no moving it around. We will gain access to the reactor vault and get the grout in there. So the calandria stays in place in the in situ disposal plan.
All right, I think that's a good one to stop at. So a lot of great questions. So thank you everybody for sending those in. So we will wrap up this webinar today. We will, like I said at the beginning, we have recorded, so we'll send out links of the recordings once they're posted on YouTube. Feel free to distribute them to anyone who might be interested. And remember that if you have any questions after this, or you think of something, or you want to get in touch, ermstakeholder@cnl.ca. So thank you, Katie and Graham, for doing this webinar, and thanks everybody for tuning in. So we will, with that, say see you next time. Thank you.